You know the feeling when you've been working hard on something for months and although you know you aren't quite there yet, all the things start to slowly fall into place and show you that light at the end of the tunnel? Well, this is where we're currently at. Okay, before we begin, let me first apologize. Actually, scratch that. Let me explain the lack of content for the past couple of weeks, and the reason is actually pretty simple. I was on holidays with my family. And since they're the ones that unconditionally support me on this journey throughout the good, bad and the ugly, I think they deserve me taking some significant time off to spend with them. Plus, my ADHD brain makes it super difficult for me to disconnect from the stuff I enjoy working on. And I do enjoy bringing this router to life, probably beyond what's considered safe for my mental health. Which is also the reason I have gone through 2 burnout periods in my career so far, and I really wouldn't like a third one, so I will take the time off when I'll need it. And luckily for me, I'm surrounded by some great people such as Aljaž, my co-founder, who's done a great deal of work while I was away. And don't worry, he too has been on holidays earlier this year in Kenya. With that out of the way, the good news first. We're done with the schematics. In fact, we overdid them a little bit in a manner of speaking. You see, with the initial prototypes, we want to measure not only the networking performance of the device, but also power consumption and the resulting temperature of the more power-hungry chips to A, make sure they all behave according to specs, and B, to discover any possible points of optimization for the final product. And for this purpose, we've probably put around 20 additional chips on the board, which brings the total number of the components to... You know what? Make a guess. How many components do you think should a router like ours have? And I'm thinking of all of them, not just your CPU, RAM and flash storage, but also resistors, capacitors, connectors, the whole lot. Now pause the video, write your answer in the comments below, then unpause for the answer. Ready for it? 1500. Yep, that's 1500 components. And speaking of components, remember how I told you in the previous update, which I'll link to up here, that I'll have an answer as to what kind of storage we're going to use on the device and how we'll use it? Well, we came to the conclusion that using eMMC is what most embedded devices go with, and well, there's a good reason for that, because they don't need any kind of special configuration or anything. You simply wire them to the CPU and it already knows how to talk to the controller that is inside the eMMC chip. But, if you remember, we only have one SDIO bus on the CPU, but 2 devices that need it, so the eMMC and a Wi-Fi card, which is why we're going to use what is called a multiplexer in 2-to-1 configuration. This chip is actually a very simple device. It splits the signal that comes from the CPU into 2 separate signals, one of which goes to the eMMC chip and the other to the Wi-Fi card. But how does it know which device to talk to at any given time? Well, for that, the multiplexer has a dedicated pin that gets connected to the CPU directly, and this pin is then turned on and off by the Linux kernel, depending on which device it needs to talk to. But there's a catch. What if a network packet arrives to the Wi-Fi card while the CPU is talking to the eMMC? Well, for that, the Wi-Fi card has a dedicated pin that is called SDIO Wake. We connected this pin to one of the interrupt pins on the CPU so that the Wi-Fi card can basically say, "Hey, CPU, I got stuff to tell you." And the kernel will then auto-magically switch the multiplexer chip to talk to the Wi-Fi card. Well, not auto-magically, we'll have to configure our system to behave like that. So make sure to subscribe because I will show you how this is done once the prototypes are ready. And speaking of prototypes, we ordered them with the sponsor of today's video, PCBway. But what kind of prototypes, you ask, given we haven't even started with the layout? Glad you asked. You see, it's easy to focus on the hardware in terms of what it's capable of doing, but it's just as equally easy to forget that said hardware runs on electricity, and that electricity gets turned into, you guessed it, heat. And since we've set ourselves to build a silent device, heat, or to put it more accurately, dissipation of it, was a major focus for us in July. We did the math, and I hope you're sitting down, because all devices combined can consume a whopping 50 watts of power. Now, don't flip the table just yet, because these are just the theoretical maximums, which we calculated literally by going through all the data sheets of each and every component and looked at their worst case scenario. Now, what are the actual chances of that happening? 0. Because in reality, under normal operating conditions, we couldn't get our reference boards over roughly 22 to 23 watts with all ports fully loaded and a stress test running on the CPU at the same time. So pretty much half of the theoretical maximums. By the way, I have to show you this. I've had this cube made just to get an initial feeling, and while I know it looks a bit crude, for a lack of a better term, it did allow me to cool the CPU passively, and while it did get into somewhere between 60 to 70 degrees centigrade, it didn't throttle or exhibit any kind of temperature-related issues. Now, why is it shaped like this? Well, the final dimensions of our router will be roughly 14 by 14 by 3 centimeters, and if we assume it'll have a 3mm thick walls, you get the total aluminum mass of the enclosure. Then I took that mass and made a shape with the smallest surface possible. Well, almost, because that would be a sphere, but given that I need to cover the whole surface of the CPU, this was the next best thing. And the conclusion of this experiment? Well, the final enclosure will most likely be perfectly fine without active cooling, given that, if our math is correct, the outer surface of the final product will be 3 times as large as of this cube. And given the cover of the case will also press against other chips that give away significant heat as well, it'll also have significantly higher thermal mass. Now, under full load, you probably won't be able to hold it for very long, but many devices of this class achieve similar temperature levels and aren't meant to be handled that often anyway. And I know what you're thinking, what about rack mounting? Well, one thing I also learned these past couple of weeks is that rack mounting also has official standards as to what kind of airflow and temperatures there should be in one. So for that purpose, we also ordered samples for both heatsinks and fans. For the latter, we are talking to one of the leading manufacturers of industrial fans, a company called Sunon. They're helping us with a somewhat custom solution because, well, we have some custom needs. You see, most industrial fans come with 3 pins. One is for ground, one is for the sense signal, which is reporting the RPM back to the controller, and finally the voltage pin that makes the fan, well, spin. And herein lies the problem. But to understand it better, let's talk about how voltage is applied to actually turn the fans, which is through something called PWM, or pulse width modulation. Fancy words aside, that just means that a 5-volt fan controller can't actually supply the fan with 2.5 volts if it wants it to spin at 50%. Instead, it will basically turn it on and off again interchangeably at a certain frequency, which we call a duty cycle. Now back to the 3-pin fans, because we're also using PWM to drive them. It means that the controller turns the fan by essentially turning it off and on again, which means that at lower speed or duty cycles, the fan simply won't have enough power to even start spinning. Now, 4 pins on the other hand mean that the fan is always powered because the 4th pin is always supplied with 5 volts, so that the 3rd pin, the one that receives the duty cycle, only takes care of the actual turning speed. And this, my dear viewer, allows us much greater control and much more precise one as well over how fast the fan is spinning, and we can get it down to 1% and it won't have any problems with that. So what's the issue then? Well, most industrial fans that Sunon has in their catalog are 3-pin only. But not all of them. And here's where they're helping us with the selection that will best fit our purpose. We're looking at 40, 35 and 30mm fans, but from the testing we've done so far, we think we're going to go with 35mm ones. Also, before we move on, fun fact for all of you PC nerds out there. A company called Fantex makes what many consider to be the best PC fans on the market, called T30. In fact, I have a couple of them cooling my development server back there, so I can confirm their superiority, and guess who they were co-developed with and are being manufactured by? Sunon. This episode is brought to you by PCBway. I've been working with them on my custom keyboard project and I was super impressed with their speed, quality and price, so I'm more than happy to recommend them to anyone who needs any kind of PCB manufacturing done, whether it's just for a couple of prototypes or if you need a larger production run. Link to their website, of course, down in the description. Back to the video. Alright, let's now talk about software, or better yet, a relatively major problem that we have with it. If you remember, I said we'd likely ship the final product either with OpenWRT or OpenSense. However, we discovered that both have pretty significant drawbacks that I want to discuss with you in this video. See, OpenWRT was built for, and it actually quite prides itself for that, for devices with very limited resources. In fact, I was able to upload it and run it from a 48 megabyte partition on the NOR flash that the development board comes with. So what's the issue then? Well, because of its tininess, it ships with a very limited set of features. That granted can be expanded upon through packages, but those packages are not all actively maintained, sometimes don't quite follow any kind of best practices, or are simply non-existent. And that's simply because nobody bothered to develop them for the WRT54GL. Remember that one? Pepperidge Farm remembers. And even the core of OpenWRT itself, at least the user interface side of things, leaves a lot to be desired. While I was on holidays, I actually attempted to at least make a nice skin for it, but to my horror, discovered, how should I put it, well, disaster that they use as a replacement for the rendering engine. You see, whenever you click a page in OpenWRT, it loads a JavaScript file that, well, moves things around on the screen. I mean, it does work obviously, but, well, pretty much throws all best practices of modern front-end development out of the window. And I can say that because I have built a front-end application in my previous company, which to this day serves tens of thousands of customers worldwide. Now, if someone from OpenWRT community is watching this and thinks to themselves, fuck this guy, what an asshole, first, you're probably right, and second, I apologize. I'm not saying these things because I want to be dismissive or belittling towards your work. Please take this as a constructive feedback and a little bit of a rant. Not because I don't care, but because I probably care too much, okay? Friends? So, if not OpenWRT, then OpenSense surely fits the bill given its powerful feature set and constant updates, right? Well, no. And not because of the software itself. I think it's actually pretty great and it runs on my home network as of right now. It's because it's built on FreeBSD, and unlike Linux, FreeBSD not only has a much smaller community of contributors, but it also doesn't run on embedded devices that well. I mean, it does run on them, but is not optimized for them. Take our CPU for example, the NXP LS1046A. We chose this particular part because it has something called data path acceleration architecture and is a special region of the CPU that does nothing but networking. This means that you can, for the most part, offload the most common hardware-intensive networking tasks to this region, leaving the general purpose ARM cores to focus either or on other tasks or do nothing, which brings the power consumption down. This is why we can blast both 10 gigabit ports with data that has to change VLANs, has to get encrypted or decrypted, get blocked by a firewall, and all that at the line speed, and all the while the CPU cores don't even stretch their legs. And by the way, we will of course test all of this in a more official capacity and present results here. And by official I mean we will hire a company that will put the device through its paces with a special network testing device called Spirant Test Center. Make sure you're subscribed because you won't want to miss that. Anyway, because of the small size of FreeBSD community, comparatively speaking, large companies don't really invest that many resources into developing firmware for it, and unfortunately NXP, the makers of our CPU, are not the exception. I mean, they do provide and maintain firmware and drivers for their platforms, but only for Linux. And that is the reason why nobody bothers to port OpenSense to ARM architectures, because it would simply not use certain features that CPUs from different manufacturers bring to the table. I mean, don't get me wrong, it would run, and there's even an official branch of OpenSense that is compiled for ARM, but all the networking stuff would simply run through the CPU cores rather than the dedicated hardware that you'd be paying for but never be able to use. So, OpenWRT is optimized for devices with constrained resources, and OpenSense is optimized for x86. Is there a third option? Yes, there is, but you're either going to love it or you're going to hate it. We build it ourselves. Now, before you react in the comments either positively or negatively, hear me out for a second. First, I'm well aware that an undertaking like this demands significant amount of resources, but given that we raised $300,000 to get this device to the prototype stage, and all the investors are fully aware that we're going to have to raise more to get it to market, I feel fairly confident I would find investors for this kind of venture. Now, I might be wrong and we might fail completely, but you have my word it will not be for our lack of trying. And second, well, I think that market could use a Linux-based router OS that is built for more powerful devices, uses more modern packages and approaches to development, and for the cherry on top, is completely open source. I mean, I could be wrong, but what if I'm right? And to that end, I have already started developing a really basic Linux distribution that's more a proof of concept at this point. I'm using a tool called Buildroot, the product of which is the base file system. The idea here is to start with all the possible programs that a router would need and test it thoroughly without a user interface. Everything needs to be done through a command line. I'll leave the link to this repository down in the description because yes, it is open source and your feedback is more than welcome. And the good news, you don't even have to have our reference board to run it. In fact, if you have a Linux machine, clone the repo and follow the instructions in the README to run it in a virtual machine software called QEMU. It literally takes just a couple of commands to get it up and running, and I'm even thinking of trying it out on a Raspberry Pi, which most of you likely have access to, and you can play along. The next step, which I haven't gotten to yet, is to build a really simple web interface that will also run on the router, and initially not do much except maybe show a dashboard and allow a user to change some trivial settings. I'm saying that because that will be enough that once the prototypes are ready, we can pitch to investors not just bringing the hardware to the market, but also our own operating system / interface. And since we're talking about hardware, I've been asked many times now whether we will open source that too, and the answer is yes and no. While I absolutely love open source, both the concept and the community, in fact I made my career out of it, the fact of the matter is that we need to be somewhat mindful of the possible consequences. And here's why. Imagine we develop our router completely in the open from day one. Everything is out there for everyone to see, use and abuse. Now, at first, nobody really cares. Most bigger companies shrug it off as something of a toy project. But at some point, this toy project starts to gain traction, grow the community, and since it's completely open, someone with significantly more resources takes what we've built up to that point and basically just invests into marketing, eating away pieces of what is called the total addressable market. And obviously, we don't want that. So, while we don't have any conclusions yet, because this is not just a decision we'll make with Aljaž, but also not only with the investors, but quite possibly a legal team, we do think that open sourcing the schematics isn't going to be that big of a deal, so we're very much inclined to do it. The physical layout, on the other hand, we will probably not. At least not yet. Not in full. Because as I just explained, the layout is basically a blueprint as to how to make a physical device, so someone can simply take it and start manufacturing identical devices pretty much overnight. One idea that we're entertaining is to open source everything once the second generation of the device comes out, provided we build a successful business by then. What we will open source regarding the PCB though is the step files so that the more creative members of the community can make their own cases. Okay, now before we wrap this up, two things. As you might have noticed, I've shown pictures of the aluminum enclosure, but not that much about the sheet metal version. That's because we simply do not have enough manpower to focus on both of them at the same time. That isn't to say that we're not thinking about it. In fact, the PCB prototypes that we designed have holes around the CPU in such a way that a heatsink can be clipped on from the top for the sheet metal version, while on the aluminum version, the CPU will be pressed against the cover and screwed onto it from the bottom side using the exact same screws. We decided to focus on the aluminum version first because both me and Aljaž have a soft spot for industrial design, and this is the version that we can really go to town with in that regard. We're calling it the Founders Edition. And now the second point, we actually already received these prototypes, but given that this literally happened 2 days ago, it technically belongs in the August report, so you'll have to subscribe not to miss it when it comes out next month. But for now, Tomáš from Slovenia, signing out.